Good morning, children. Today we're doing related grades. What are you doing today? What are you doing today?
Related, right?
Great. Now let's start. Start off with a very difficult problem, okay? Difficult problem. So we have to solve of the rate of change of the distance between the two girls. And since the path to which they're running to herself is perpendicular, we can actually form a right angle triangle, and we can solve C for that, and then we can solve dc over dt, which is the final step of the problem. And we know dA over dt, which is dA over dt is equal to negative 17.854 meters per second. It is negative because the distance is decreasing and they're running towards herself, not away from him, so it will be negative. And we can do the same thing for B. dB over dt is equal to negative 15.331 meters per second. And so the Pythagoras theorem, c square is equal to a square plus b square, and a here is pi meters, and b here is e meters. So we do this, c is equal to pi square plus e square. And to find dc over dt, we need to differentiate this using chain rule. dc, 2c, chain rule, since 2c and then dc over dt is equal to 2a dA over dt plus 2b dB over dt. So we can plug in the values of A, dA over dt, B, and dB over dt, as well as C, since we solve it here. So we can divide both sides by 2 times this value. So the dC over dt equals this over this, which is, using my TI-84 Plus C Silver Edition by Texas Instruments, available in all retail stores, you get the value of dC over dt equals 6.940 to 3 decimal places meters per second, and there you go. Why are we late? You know what? You know why you have to melt it? Calculus!
What?
You can figure out why your ice cream melted by calculus.
What?
Yeah. Experiment, go.
So now, you want to know why your ice cream was melting at such a fast rate because of this little puny hole in the bottom, and it made you very, very sad. So, now we are going to solve for the change in the volume of the cone. Now please disregard the circle on the top because nobody got no time for that. So, we're going to say that the top, the radius at the very top of the cone, we're going to say that it was approximately 4 centimeters. And then the height, assuming the cone was full, not including this huge thing at the top because we take our time. We're going to assume the height at the top equals 16 centimeters. Perspective simple. And then we all know that the volume of a cone is V equals 1/3, because it's a cone, not a cylinder. It is 1/3 pi r squared h. Now, usually for related rates, you just differentiate both sides and plug in the known values. But you see, when we solve for volume, we have two variables, and it's terrible. Now, to simplify that, we are going to put this as one variable. And as you can see from here, r to h is 4 to 16. So r to h equals 4 to 16, which equals 1/4. So that means that r equals 1/4 of the height. And we can plug that back into your original equation for 1/3 pi, oops, because you're substituting in r, so you don't need to put that back. So 1/4 h squared times h, which simplifies even more to 1/48 pi h cubed. Now, let's just say that at certain time t, we'll say time equals 7.26 seconds, because everyone likes nice whole numbers. We're going to say that the height is changing at a rate, so dh dt equals 1/2 centimeter per second. So it's draining and the height is changing at approximately 0.5 centimeter per second at time t. And then, here's where the fun differentiation comes in. So, now you have this and you have your given h, and we are solving for dv dt. So if you differentiate this equation, this will go into dv over dt equals 1/48 pi. That does not change because it's constant. Now you use this fun little derivative rule for h, and then you have to have h prime. But h prime equals dh dt. So let's just do this for sake of consistency.
And then to simplify, even further, 2 becomes 1/16 pi h squared dh dt.
So now you can plug in your known values, because we know h equals 8 at certain time t. So 8 squared, and we just established that dh dt equals 1/2. So we plug that in, and when you simplify it and cancel it all out, it becomes 2 pi centimeters cubed per second, and there's your answer.
So we're trying to solve for the rate at which h decreases out of the bucket. Because the radius is not constant, we'll have to model this problem with the frustum. Though it will take extra steps, it's not that much harder than the ice cream cone problem. If you could imagine extending out the sides of the bucket, you'll see that the volume of the frustum is equal to the volume of the big cone minus the volume of the little cone. We are first going to find the volume of the little cone, which is going to stay constant. Doing this takes a little bit of geometry and algebra, but it's not too hard. Using similar triangles, I found that the height of the big cone is 18.529 centimeters. Plug that in, and now you know the volume of the small cone. To find the rate at which h increases, we'll need to separate the variable. Using a triangle, we'll find that r equals 2.49h. We'll substitute that into the equation and simplify. After deriving the whole thing, we'll plug in dv dt, h, and then we'll be able to find dh dt.
Ready, go!
What are you doing today?
Related, right?
Great. Now let's start.
Derivatives.
Shut up.